It is important that the technician understands the effects of sensible and latent heat on the mechanical refrigeration system. Heat is a form of energy. Energy can be converted to another form but not created or destroyed. How do we measure heat? A thermometer? No. A thermometer measures heat intensity, changes in temperature. We measure heat in BTUs, British thermal units. Let's look at some facts. Let's review the types of heat. Sensible heat. Heat which changes the temperature of a substance without changing its state. Latent heat. Heat which changes the state of a substance without changing its temperature. What is saturation? The state or process that occurs when no more of something can be absorbed, combined with, or added. Simply put, when one substance holds another substance at the same temperature and pressure. An example, the tank of refrigerant has liquid refrigerant and vapor refrigerant in it, and both have the same temperature and pressure. Note the volume and pressure of both will change with temperature. Another example, a sponge is saturated when it holds 100% of the water that it can, and any additional water will drop out of the sponge or not be absorbed by the sponge. We will use water as an example to understand the effects of heat on a substance. Specific heat of a substance is the amount of heat in BTUs required to raise 1 pound of a substance 1 degree Fahrenheit. The specific heat of water is 1 BTU per pound of water. All refrigerants have a specific heat. What will happen if we continue to heat water? From 32 degrees Fahrenheit to 212 degrees, water absorbs heat. The water molecules gain kinetic energy and move around faster. The temperature rises from 32 degrees Fahrenheit to the boiling point of water, 212 degrees Fahrenheit. At 212 degrees Fahrenheit, water starts to boil. Does the water disappear? It does not disappear. The water changes into steam. This process is called vaporization. During the phase change, the temperature remains at 212 degrees Fahrenheit. Let's look at the saturation of water. Water at standard air is saturated at 32 degrees and 212 degrees Fahrenheit. Standard air is air having a density of 0.075 pounds per foot, which approximates air at 68 degrees Fahrenheit dry bulb and 50% relative humidity at a barometric pressure of 29.9 inches of mercury, or approximating dry air at 70 degrees Fahrenheit at the same pressure. At 32 degrees Fahrenheit, do we have water or ice? At 32 degrees Fahrenheit, in order to change from water to ice or from ice to water, we must remove or add latent heat. At 212 degrees Fahrenheit, do we have water or steam? At 212 degrees Fahrenheit, in order to change from water to steam or from steam to water, we must remove or add latent heat. The following graphs will help you to better understand the effects of heat. We have taken a thermometer and bent it at the saturation points. The vertical lines represent sensible heat. The specific heat of water is 1 BTU per pound and remains water from 32 to 212 degrees Fahrenheit. The specific heat of ice is 0.5 BTUs per pound and remains ice below 32 degrees Fahrenheit. The specific heat of steam is 0.48 BTUs per pound and remains steam above 212 degrees Fahrenheit. The horizontal lines represent latent heat. Latent heat of fusion, temperature remains constant as solid turns to liquid or liquid turns to solid. The latent heat of fusion is 144 BTUs per pound. Latent heat of vaporization or condensation. The temperature remains constant as a liquid turns to vapor or a vapor turns to a liquid. The latent heat of condensation or vaporization is 970 BTUs per pound. Using the following formulas, one can calculate how many BTUs are required to raise or lower the temperature of a substance between any 2 points. Each line on the temperature heat chart must be calculated separately and added together in order to obtain the total heat content of a substance. The sensible heat formula is the quotient, or BTUs, in pounds times the temperature difference times specific heat. Let's look at an example. How many BTUs are required to change 10 pounds of water from 32 degrees to 212 degrees Fahrenheit? So therefore, BTUs is equal to pounds times the temperature difference times specific heat. Filling in the numbers, we have 10 pounds times 180 degrees times 1, which is the specific heat of water, which gives us the total BTUs of 1,800. The latent heat formula is quotient, or BTUs, is pounds times specific heat. Let's look at an example. How many BTUs are required to change 10 pounds of water from 212 degrees to steam, which is also 212 degrees? Therefore, BTUs is equal to pounds times specific heat, or BTUs is equal to 10 times 970, which is the latent heat of fusion, and therefore the BTUs is 9,700. The addition and removal of both sensible and latent heat are critical to understanding the mechanical refrigeration system. In the evaporator, approximately 85% of the entering refrigerant is liquid. Sensible heat is added to the liquid refrigerant to get it to its saturation. Latent heat is added to the saturated refrigerant to change its state to a vapor. Sensible heat is added to the vapor, which is now superheated. In the condenser, the entering refrigerant is superheated vapor. Sensible heat is removed from the vapor to get it to its saturation. Latent heat is removed from the saturated refrigerant to change its state to a liquid. Sensible heat is removed from the liquid, which is now subcooled. Let's look at the two other components of the mechanical refrigeration system. First, the compressor, which increases low-pressure superheated vapor to a high-pressure superheated vapor. Superheat is increased approximately 20 to 25% due to the heat of compression. Next, the metering device reduces high-pressure subcooled liquid into a low-pressure subcooled liquid. Approximately 12 to 20% of the liquid flashes to a vapor, thus reducing the pressure as it passes through the metering device. Just to repeat, the four basic parts of the mechanical refrigeration system are the compressor, the condenser, the metering device, and the evaporator. We must connect all these parts with refrigerant lines. Let's identify the lines. The discharge line, which connects the compressor with the condenser. The liquid line, which connects the condenser with the metering device. The liquid line after the metering device, which connects the metering device with the evaporator. And finally, the suction line, which connects the evaporator to the compressor. Now let's look at the condition of refrigerant in the lines. The discharge line is a high temperature, high pressure, superheated vapor. The liquid line before the metering device is a high temperature, high pressure, subcooled liquid. The liquid line after the metering device is a low pressure, low temperature, subcooled liquid. And the suction line is a low pressure, low temperature, superheated vapor. The vertical line which I have drawn depicts the separation between the high and low sides of the system. The horizontal line which I have drawn depicts the separation between the liquid and the vapor sides of the system. There are two measurements which the HVACR technician uses in diagnosing refrigerant issues. Superheat, the amount of sensible heat added to the refrigerant after it has vaporized. Subcooling, the amount of sensible heat removed from the refrigerant after it has condensed. Let's look at the procedures for determining superheat and subcooling. For this demonstration, we will use 410A as a refrigerant. Connect the low side gauge to the low side of the system. Note the pressure on the gauge shows 118. Connect the high side gauge to the high side of the system. Note the pressure on the gauge shows 340 psig. Connect the temperature sensor to the suction line. Note the temperature is 50 degrees Fahrenheit. Connect the temperature sensor to the liquid line. Note the temperature is 90 degrees Fahrenheit. The formula for superheat is actual temperature minus the saturated temperature. To obtain the saturated temperature, we use the pressure temperature chart for the refrigerant in the system. Filling in the numbers and doing the math, we have 10 degrees of superheat. The formula for subcooling is saturated temperature minus actual temperature. Again, we use the pressure temperature chart to get our saturated temperature. Filling in the numbers and doing the math, we have 15 degrees of subcooling.